All right, today we're talking about lecture 15, which will be weighted graphs and Dijkstra's. We're going to talk about the definition of what a weighted graph is. We'll talk about the examples. We're not going to talk about representation. We're going to cover that in homework instead. And then we're going to go and look at the problem of the shortest source, the single source shortest path. We're going to look at the problem statement. We're going to look at some examples. We'll play around with that a little bit. And then from there, we're going to look at Dijkstra's. Dijkstra's is a very famous algorithm on trying to find the shortest distance between A and B. Give me a yes in chat if you've seen Dijkstra's before, or no in chat if you haven't. I'm just curious. Who's seen Dijkstra's before? We're seeing mostly no's in chat, which is fair. It is something that you should learn in this class. So if you haven't seen it before, it's not like a big deal. So I'm glad that this is new news for you, right? If I'm being honest, Dijkstra's is kind of hard to teach. Getting this right is a little bit of a challenge, and so we're gonna actually have an entire homework dedicated to it so that you actually learn Dijkstra's properly. But for now, I'm gonna try my best to get through it. If you have any questions about Dijkstra's, please ask. But we're gonna focus the most of this lecture just on this one algorithm and make sure we understand it well. And then from there, we'll go in and sort of hopefully you'll feel good about this algorithm going out. All right. So let's start with weighted graphs. The big idea around weighted graphs is that you have a normal graph. So it has some vertices, it has some edges. And each of the edges now has a weight on it. In other words, it has a number associated with it. And that number could be positive, negative, or zero. This is useful for representing distances between places, costs between servers on a network, people who owe each other money. So any sort of relationship in a graph that requires some sort of numeric value assigned to each edge can now be represented using a weighted graph. The most common problem we care about is pathing, the idea of like, how do I get from A to B with the least cost? So if you think about Google Maps, for example, it's not that every edge in the graph is just like one, right? The distance to get from San Francisco to Atlanta is a lot different from getting to from San Francisco to LA, right? The difference between getting from San Francisco to LA is going to be a lot. It's going to be a lot shorter to get to LA than it is to get to Atlanta. So if you were to represent this on a graph, the edge from SF to LA should be shorter or have a smaller weight than the edge between SF and Atlanta, right? Across the country versus down a state. And again, we're to the point of the class where if you just keep track of all the terms and keep them straight in your head and you know how to apply them step by step, then you should be feeling good about the exam, which is next week. We'll talk a little bit about the exam soon, but for now, we're going to dive right into graphs. So we're going to go ahead and take a look at this weighted graph. You can see here that all of the edges now have these blue numbers associated with them. And we're going to take about 10 seconds to answer each of these questions. So we're going to take 10 seconds to think about what is the shortest path between this node 1 and this node 5. All right. Go ahead and take the time to figure that out. What is the shortest path between 1 and 5? What would we say here? Okay, a lot of people are saying we'll go from 1 to 3, 3 to 4, and then 4 to 5, which makes sense because if you think about this path, well, the cost to get from 1 to 3 is 1, plus another 1 here, plus another 2 here, which means if we do 1, 3, 4, 5, that'll be cost 4 because we just take all the weights on the edges and add them all together, right? If we were to try to do something else, let's say 1, 2, 4, 5, that's going to have a cost of 5 because we have this edge here, 1, plus 2 here, plus 2 here. So this would be more expensive, so we don't want that. Likewise, if we wanted to go from 1 to 0 to 2 to 4 to 5, that would be like cost 10, I think, which would be even more expensive. So ideally, if we want the shortest path, what we mean is the path with the least amount of cost across all the edges, which in this case means going from 1 to 3, 3 to 4, and 4 to 5, right? Let's just do another one real quick. What's the shortest path between 1 to 2? It's just 1 to 2, right? Like there's no scary part from it for it. We would have 1 to 2, and it would be cost 1, right? But let me go ahead and turn that on its head. Let's say we went and had 10 here instead of 1. Let's just imagine for a second that we had 10 here. If that's the case, what's the cost? What's the new path if this was 10 instead of 1 to get from 1 to 2? What would be the shortest path there? I'll give you 10 seconds. Just think about it for a second. Okay, or type it into chat. So people are saying instead of going directly from 1 to 2, we want to go instead all the way around because this is going to be the cheaper cost, right? So the idea here is the shortest path between 1 to 2 would be 1 to 2 normally, but if we made the weight, if we weighted the edge more heavily so that this is a 10 instead of 1, then we want to go all the way around because the cost to get from 1 to 3 to 4 to 2 would give us cost 4 versus this cost 10 by going directly there, okay? And another one that I didn't mention, let's just imagine we go back to the original graph, but let's just imagine what is the cost, what is the shortest path between 1 and 1? If we want to get to the shortest path between 1 and itself, I'll give you 10 seconds to think about it. What do you think that looks like? Go ahead and type in chat. What's the cost to get from 1 to itself? Okay, if you're confused, question mark. Otherwise, okay, people are giving me a bunch of different answers. So some of you are like, okay, do we have to go away from the node? Maybe we have to go in this direction and then go into a loop. And some of you are like, oh, this, I have no idea. And then some of you are like, oh, the cost is probably going to be 1, right? So what is the shortest path between 1 and 1? There's no path. You're already there, right? So cost 0. So this is a little bit of a definitional problem where, you know, depending on how you define things, you could say that the shortest path is just the empty path. And that's what we're going to say here, right? So we want to say that if you are, for example, in your house and you open up your GPS and then you type in your house as the destination address, well, the destination, like Google Maps, is going to tell you you're already there. You know, the distance to get to your house is 0, and therefore, you know, the pathing is also just the empty. Like you don't have to take any other nodes. You're already there. Okay, so you could say that it's just you're already there. There's not really an obvious way to represent it. You might have the empty set. You might have 1 here, but in short, if you're in if you're in the place that you want to be, then the cost is 0 to get there. What about checking for cycles? So we're going to assume for a second here, we're just going to assume that all edges are positive here. All right, that's going to help us later on. We're going to assume right now that we're dealing with edges that are all positive, and that's going to be important later. All right, hopefully that answers your question. If you're not, if that doesn't, just ask a follow-up and I'll be happy to help. Someone's asking, what is the, I'm asking, what is the shortest path between 1 and 6? Now, one thing to note is that the shortest path between 1 to 6, you notice that 6 can only get, we can only get to 6 through 5, right? What would we say the shortest path from 1 to 5 would look like? What was the cost of that? Go ahead and type in chat. What was the shortest path from 1 to 5? It's 1, 3, 4, 5, right? This one up here. So the shortest path between 1 to 6, shortest path between 1 to 6 is equal to the shortest path between 1 and 5 plus the edge between 6 and 5 and 6, right? So in other words, we can break this problem down a little bit by saying the way to get to 6 is through 5. And since we know the shortest path to 5, the only thing we have to do is to add the edge to 6, right? This is going to be super important in a second. Someone asked, if an edge is negative, does that subtract from the path cost, or isn't it not traversable? It does subtract from the path cost, and we're not going to talk about negative edges right now. We're going to assume that all edges are positive. In other words, it can't be 0, can't be negative, right? You're bringing up a really good point. We're not going to cover it right now. We'll cover it after the exam. I wanted you to worry about less things for the exam, so we're going to ignore the idea of negative edges right this second. Now, lastly, what is the shortest path between 1 and 8? I'll give you 10 seconds. Let's think about this. All right, what do you think? How do we get from 1 to 8? There is no path, right? A lot of people are saying no path. In other words, the cost is infinite, right? If there is no way to get from 1 to 8, then we want to observe, or we want to note that the cost would basically be infinity because there's literally no way to get from 1 to 8, okay? Need a Stargate, need a kayak. Yeah, you need some way to hop over the edge without being able to do that. So hopefully now you have an intuition of what pathing looks like. We're going to go ahead and look at the formal definition now, the formal problem we're going to try to solve. This is called the single source shortest path. What we're going to take as input is a weighted graph, v comma e, where the weights of all the graphs, of all the edges are positive, right? As we said before, we're assuming all edge weights are positive. In other words, it can't be 0 and it can't be negative, right? That's going to be really important for this lecture. G could be directed or undirected. We don't really care. But we also need as input a source node S. In other words, a node that we start from. This is literally just a node that we start from. So weight is equal to length. You can think of weight as length, or you can think of it as time, or you can think of it as anything else. It doesn't translate to a direct physical analog sometimes. Like, for example, if we have a directed weighted graph, let's say we have a graph A here, and then we have a graph node B. Let's say that I owe my brother $400, right? I don't. But let's just imagine that we did. So the edge here could be negative 400. And it wouldn't be a length here. It would just represent some value relationship between A and B, right? My brother and I both have expensive tastes. So I've like bought him expensive things in the past, and he's bought me expensive things in the past. So we have owed each other that much amount of money in the past. It's really weird, but I don't know. But the output here for the single source shortest path, given a weighted graph, which could be directed or undirected, and a source node S, is two things. It's going to be an array distance where every node, every element in the array describes the shortest distance between S and U for some reachable node U and B. And we're going to also have an array prev, where prev is the previous node along the shortest path between U and B. This is actually so important that I need you to write it down. We're going to write it down as well. We're going to say that distance is equal to distance of U is equal to the cost of the shortest path between S and U. You should be writing this down with me. And distance of prev of U is equal to the previous node along the shortest path between S and U. Okay? So things we care about. We assume that all edge weights are positive, right? And also that the distance of U and the prev of U, this definition we're going to keep here, all right? And then we know that S is going to be equal to the source, which is the node that we start from. Here are the three things we need to remember going forward into the next slide. So let's go ahead and look at an example. What is the shortest path from S to, if we say that S is equal to 1? So what we're saying is that the distance, like we will care about this node here, and we want the shortest path between this node and every other node that we could possibly visit. All right. So we don't know what distance and prev will be. We're going to try to figure this out, and we're going to try to figure this out by hand together. So distance is going to have at the beginning, how many elements do you think we'll have? Go ahead and take 5 seconds to think about it. What do you think distance will be? We covered this, I think, in the previous slide. Go ahead and type in chat. What do you think? How many elements do you think distance will have? Some people are saying 7. Some people are saying 0. Some people are saying 9. Some people are saying question mark. Very good. All right. So in this case, I'm going to go ahead and say that distance will have basically 9 elements, one for each node in the graph, right? So there's going to be as many nodes in distance as there are elements in the graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And prev will be much of the same. Prev will be all of these elements here. Okay. The reason why we have 9 is we don't know whether or not we can reach 8 from 1, right? We have no idea. So some people are saying 7 because they know that you can't reach this node and this node from 1. But from an algorithm's point of view, or from the problem solver's point of view, we won't know that. All right. So type in V in chat for the number of nodes in this array if you feel good about that idea, that we don't know whether or not we can reach 7 and 8 here, and therefore it should give us 9 elements. We should have distance equal to an array of 9 elements, one for each node that we could possibly visit, even though we can visually inspect and see that some of these right now we actually can't reach. Okay, so now let's just try to figure this out one step at a time manually. We said previously that the distance from 1 to itself should be 0. So what we're going to do is that at index 1, I'm going to put a 0 here to represent the fact that it doesn't take much time. It doesn't take any time at all to get from 1 to itself. The distance to get from 1 when you're starting at 1 is 0. All right. Give me a 0 in chat if you remember that. Give me a question mark if you're not sure why I'm putting a 0 here. Remember, each of these elements here describe what's the cost, what's the distance to go from that node to itself. Or sorry, that node from S to that node. If we say that we start at 1, if the node that we're trying to start from is 1, then we want to say what's the cost to get from 1 to 3? What's the cost to get from 1 to 2? What's the cost to get from 1 to 0? What's the cost to get from 1 to itself? Well, the cost to get to 1 from itself, if you start at 1 and you end at 1, then you don't have to go anywhere, and therefore the cost should be 0. The corresponding element in prev will be set to null because in the path, there was no previous node you had to go to in order to reach S, right? In order to reach the node that we care about. If we start at 1 and we end at 1, then there is no previous element. Let me make this a little bit more clear. Okay, the shortest path between 1 and 3 is clearly this edge, right? We just take this edge here. So if I go to index 3, I can go ahead and put a 1 here to indicate that the cost to get from 1 to 3 is 1. And then I'll put a 1 here as well, saying that in order to get to 3, to get from 1 to 3, we have to go through 1 in order to get to 3. The last element we reached was 1 when we got to 3. Now, that might not be obvious, so let me go and fill this in some more. I'm not filling it in the order that we would do it in an algorithm. I'm just doing it manually, all right? If we go from 1 to 4, which node are we going to visit right before we visit 4? If we go from 1, what's the path to get to 4? What's the node that we have to visit right before we visit 4? Right? The path is 1, 3, 4. That's the cheapest path, right? It's cheaper than 1, 2, 4, and it's cheaper than 1, 0, 2, 4. So the node that we visit right before we visit 4, if we're going from 1 to 4, is 3, which is why at element 0, 1, 2, 3, 4, we're going to put a 3 here. And the cost will be the cost of this edge plus the cost of this edge, which is 2. All right. If you feel like you understand that, I'll give you 10 seconds. What do I do for 5? And what do I put here for 5? Right? If you're following along, this is a check for your understanding. What do you think 5 will be for distance, index 5? And what do you think prev will be for index 5? All right, go ahead and type in chat if you have it. The cost to get to 5 will be 1 plus 1 plus 2 here, which will be 4. And the previous node we visited would have been 4, right? I had to go through to node 4 in order to get to node 5. All right. If that's the case, well, if we keep going, what is the cost to get from 1 to 0, right? I'll give you another 10 seconds. If you really are following along, you should be able to get this one too. It's a little bit tricky, but hopefully everyone's thinking along the same lines. Okay, what do you think? What's the distance to get from 1 to 0? It should be 3 for the distance, because we want to go from 1 to 2 to 0, right? Instead of going from 1 to 0, because that would be more expensive. And then that means that the prev here should be 2, because we went through 2. The last node we visited before we visited 0 was 2. All right, so the 2 in prev indicates that we went 1 to 0. And then the 3 here indicates that it costs us a path. The path cost was 3 total. All right, the cost to get from 1 to 2 would be 1. And there's a 1 here to indicate that we went through node 1 in order to visit node 2. What do you think the cost for node 8 will be? What do I put here? I'll give you 5 seconds to think about it. Based on what we saw before, this should hopefully be straightforward. And someone's already spoiled it in chat, so type it in if you have it. Right? It should be infinity. This should be infinity because there's no way to get from 1 to 8. Likewise, there's no way to get from 1 to 7, which means that there should be a null here and a null here as well, right? Because there's no way to get from 1 to 7, and therefore there's no path, which means that the previous node that we reached in order to get to 7 is null because it doesn't exist. Same argument for 8. Now, last one, I'll give you another 10 seconds just to make sure we're all on the same page here. What is the path from, what is the distance cost it will be to go from 1, s is equal to 1, all the way up to 6? And what do you think should go into the corresponding prev slot? How would you represent infinity in code? It would be integer.max max value, I believe. All right, so the question is, if we're trying to get from 1 to 6, what would be the cheapest cost to get from 1 to 6? And what's the node that we would have to put here? Go ahead and type in chat. So the distance should be 9 because we have the cheapest way to get to 5, which is 1 plus 1 plus 2. And then we have to add this additional cost of 5, which we can't circumvent. This edge here costs us 5, and that's the only way to get to 6, which is why we end up with 9. 4 in order to get to 5, and then this 5 here. And then the prev here should be 5 because this is the node 5 here that we visit in order to get to 6, right? So everything in prev is going to be a node label. And then everything in distance is filled with costs, all right? So it's super important that you keep that in mind as we're working through this, because we're going to see distance and prev over and over and over and over and over again, all right? Now, the reason we care about prev so much, the reason why it's actually important to have prev is that it actually can reconstruct the path to go from node S to any other node in the graph, the shortest path. So for example, if we want to reconstruct the path from 1 to 0, what we're going to do, let me just write this out. Say we wanted the path from 1 to 0, right? We wanted the actual nodes that we visit. How do we use prev for that? Well, what we'll do is we'll go into index 0, because that's the destination where we care about. We'll grab the 2. We'll realize that the node that we will reach right before 0 will be 2, all right? Everyone see where we're at so far? Give me a 2 in chat if you see how we got this 2. We're trying to create the path here. So now we take the 2 and we look into the index. We say, okay, well, at index 2, what is the node that we visit at before that, right? The node we visited before 0 was in node 2, and the node we visited before 2 was node 1. So we're working our way from back to front working our way backwards to reconstitute the path to go from 1 to 0. Now, if we go and now look, okay, this had 1 in it, which means when we now go to index 1, we see there's a null. That must mean that we're back at the beginning and we're done because there's no other nodes to add to this path. And so this is the one that we have. Okay. If we wanted to do the same thing from 1 to, let's say, 5, that's going to be more involved, right? So what is the first index that we look into, and what is the next index that we look into for the path from 1 to 5? So we're trying to get to 5 starting at node 1. We're going to try to find the shortest path to get there. My question is, what is the first index that we look into for prev in order to figure this out? And then what's the second index based on the information we see there? I'll give you another 5 seconds. Okay, go ahead and type in chat. Which index do we care about? Okay, we got a bunch of question marks. We got a bunch of 6s. We got a bunch of unsures. Okay, cool. I'm glad we did this. Since this is node 5, we're going to look at index 5. So 0, 1, 2, 3, 4, 5. This is index 5. So my question was, what index do we look into prev in order to grab the element? So index 5 is the first index we look for if we're trying to find the path to go from 1 to 5. This will let us realize that first, there is a path because we know 5 was the last node that we visited. And right before that, there's a 4 in this slot, which means that we then look at index 4 as the next node we care about. Right? How did we get to 4? We looked and found index 3. All right, give me a 3, 4, 5 if you understand the lookup pattern that we just described. We started at index 5. We said, okay, in order to get to 5, we had to visit 4. Well, how did we get to 4? We had to visit 3. Well, how did we visit 3? We look at index 3. We realized that we had to visit 1. And then when we look at 1, we realize that 1 is null, and therefore we're done. Okay? So in other words, and you should take this down for notes if you didn't follow along the first time, which I think a lot of you didn't, was we look up index 5 to find out which node we visited before node 5, right? That gave us 4. And then we look up index 4 to find out what node we visited before index 4. That gave us index 3, right? And then we look up index 3 to find out which node we visited before node 3, which gave us 1. And then lastly, we looked up index 1 to find out if there's a node that we need to visit before node 1. That gave us null, which meant that we're done, right? We figured it out. We stop when there's a null before the first. Yeah, we in this case, we're stopping when we reach a null because that indicates that we've reached the beginning of our path, right? Because we're explicitly saying that null either represents that we can't get to that node or that this is the first node that we started at, right? Index 1 has no previous node because that's the node we start at, which is why this is null. And you can see based on the cost here, since it's 0, that this must be the place where we started at because the only place that costs us 0 is ourselves. If I start at S and I end at S, then the cost should be 0. Every other place should have a positive cost because we assume that all edge weights are positive. So anytime you traverse an edge weight, you're only increasing your cost. Great question. Nodes as characters instead of ints would be a little bit easier to learn. I see. Yeah, this is the way we normally represent it in the code. So we could have A, B, C, D here instead. So someone's saying, hey, if we labeled these A, B, C, D, it might be easier to keep track of things. I'm not gonna, all my slides use numbers, so I apologize because it'll take you a little bit of effort to translate it. But I agree with you that next time we'll use letters, and that'll probably help out. Okay, but I wanted to show you the direct correlation of the distance and previous arrays. Normally we use arrays to indicate node 0, node 1, node 2, node 3. Just like in the previous lecture when we had visited, we also had an array of visited nodes where the index represented the node we cared about. It's a fair point, but we want to strike a balance between easy to understand and easy to code. Right now, I'm biasing toward easier to code. All right, let's move on. So here's a question. How do we actually come up with an algorithm to solve this, right? Like we're going to need to figure out how to solve this by hand, which is kind of a pain. We want an algorithm to find the shortest path from a single node to all other nodes that are reachable from that node. In order to be efficient, we want to visit every node and every edge, ideally only once. And how do we solve this by hand? Well, I'm going to go ahead and show you something silly. And I'm showing you something silly because you're going to remember it because of how silly it is, right? I tried to teach this a couple of different ways last semester. I found that introducing you to a silly approach first and then showing you the actual code helps it stick in your head a little bit more. I'm hoping this will be true this semester as well, okay? So here's the approach. If we're trying to find the shortest path for s is equal to 1, notice this is the same graph as before, but I've made it a little bit smaller so that we can work through the example a little bit faster. We're going to try to manually solve this one step at a time. Here's the steps. We're going to let George, we're going to call a node George, and George is going to be the next unvisited node closest to S based on distance. All right, that's a mouthful, but George will be the next unvisited node closest to S based on distance. So we're going to visit all of these nodes, and as before, we're going to mark them as visited or not. And George will just be the first node that is closest to S based on distance. Now, if S is equal to 1, and we're starting at the very beginning of this approach, what would be the next unvisited node that's closest to S based on distance at the very, very beginning? Go ahead and take 5 seconds to think about that. Okay, people are saying either 2 or 3, so go ahead and punch in chat if you haven't. Thank you for falling into my trap. The correct answer here is 1. The closest node that we haven't visited is the node that we start with because the distance to get to that node is 0. So at the very beginning, the first George will always be S. Yes, it was a cheap shot. I'm making this a big deal so that you remember it. The more I kind of trick you, the more you're going to remember it for the exam, right? That's kind of the goal here, to get baited so that you don't fall for the same trap on the exam. GSU refund, please. Oh, oof. All right. The next thing from there is we're going to look at all of George's neighbors, and then we're going to update the distance for them if we need to. And then we just pick a new George after that. We do that until we run out of nodes to visit. Okay? So everyone just take 10 seconds to digest this. We're going to try to find nodes based on the next unvisited node to closest to S based on distance. So we're calling that George. We're going to look at all of George's neighbors, and we're going to update the distance for them if they're needed. And then otherwise, we're going to pick a new George, right? Like after that, we'll pick a new George. All right, so let's just actually try to solve this for S is equal to 1. So this should look very similar to what we had before, right? We know that what we want is that distance in this case will be equal to the following, right? The distance, there's going to be 6 nodes here, right? Because there's only 6 nodes in my graph. So there's going to be 6 slots here. The distance from 1 to itself will be 0. The distance from 1 to 2 will be 1. The distance between 1 and 3 will be 1. The distance between 1 and 0 will be 3 because we go from 1 to 2 to 0. The distance between 1 and 4 will be ideally 4. And the distance between 1 to 5 will be infinity, right? If you followed all of that, take 15 seconds to tell me what prev will look like. Do I mean 2 for 4? Oh, yeah, it should be 2 here. My bad. Thank you. I do mean 2. Correct. I'm glad that some of you caught that. Or maybe all of you felt confused, in which case, great. That was an honest mistake. I'm going to give you 15 seconds now. Tell me what prev will look like. All right, what do we have here? Type it in chat if you have it. So we know that in order to get from 1 to 0, we're going to have to go through 2, because that's what we said before, right? The cost to get from 1 to 0 should be 1 to 2 to 0, which gives us cost 3. So we go through 2 in order to get to 0. We go through nothing to get to 1 because we're already there. We go through 1 to get to 2. We go through 1 to get to 3. We go through 3 in order to get to 4. And we don't have any way to get to 5, so there's a null here as well. All right, so this is what we want. However, what we start with in this case is we're going to start with distance is equal to a bunch of infinities. And prev will be equal to a bunch of infinities. Or not a bunch of infinities, there'll be a bunch of nulls. All right. At the very beginning, we know nothing about nothing. So our silly approach starts by assuming we know nothing, right? Now, the first node that we can update, though, is node 1. By definition, because 1 is the source, right? That means that here, what we're going to do is we're going to look at index 1 and change it to 0. And we get that for free, right? So we'll go ahead and write that down. Distance of s is equal to 0 always, right? That's something to note. And I'll put that up here so that you remember. This is all of our useful information that we're going to keep throughout all of the slides. And this is going to be the next one here. All right. So I'll just include this. Actually, no, this is better. All right. So from here, we pick the first George. As I said before, the George will depend on the next unvisited node that's closest to S. In this case, George the first is equal to node 1. Everyone type in all hail George the first to celebrate his coronation. All hail George the first. We have picked our first George. Right? George is going to be this next unvisited node closest to S. That means that according to distance, the node that's closest to S right now is index 1, which has a cost of 0, which means that this node here is going to be our first George. Okay. Now we're going to go ahead and look at all of George's neighbors and update distance for them if we need to. In other words, we're going to look at node 0 first and say that the distance to node 0 from node 1 will be, in this case, 4. All right. We're going to update it because before the cost to get to node 0 was infinity. So literally anything is better than infinity. So even though you can visually see that there's a cheaper path, the only path we know of so far that actually gets us from 1 to 0 is one that costs us 4. All right. And we replace the corresponding null here with a 1. All right, so we replaced the infinity with a 4 because we wanted to update the distance between getting from 1 to 0 is now cheaper than it was before. It used to be infinity, now it's 4, right? It's not the cheapest it could be, but it's the cheapest we've seen so far. So type in 4 is the cheapest so far if you follow, question mark if you're confused. Why that we updated index 0 to have a 4. 4 is the cheapest so far. All right, great. Right? If you're genuinely confused, type a question mark. I need you all to get this. Otherwise, it's going to be really hard for you to do the homework. All right, cool. So that was the first neighbor. We're going to keep going. And then if you're still confused at the end of it, I promise there'll be more resources to help you out. We'll also talk about it in the break. The next thing we care about is node 2, because that's the next neighbor that we have of node 1, the next neighbor of George. And we're going to do the same update. So previously, the cheapest way to get to node 1 was an infinite, right? There was no way to get to node 1. And therefore, this prev also had a null here. Now we realize that getting from 1 to 2 can be cheap. It can be as cheap as saying it costs us 1 to get there. And the way to get there is through node 1. Okay? Now, I know some of you are a little bit confused. That's fine. I'm going to keep going. And I feel like if we keep going, it'll help you. But if you're still confused after everything, we'll talk about it. All right. It's okay to be confused for this algorithm. It's a lot of moving parts, which is why I'm doing this silly example. Now, the last thing we do here is we update the last of George's neighbors, in which case we change index 3, which represents the cost to get from 1 to 3 to 1, because we know we can just take this edge directly. And we can update the node we visited right before we got to 3 was 1 as well. Okay, so that was the first George. Now we're going to have to pick the next George based on the distance array, what is closest and what we haven't visited. We just visited this George. We visited node 1. What is the next nodes that could possibly be a candidate for the next George? Right? If George is the next unvisited node closest to S based on distance, I'll give you 10 seconds. What do we think are the next Georges that we could possibly pick? All right, type it in chat if you have it, right? Question mark if you're unsure. If you don't know why people are typing in 2, 3, question mark is fine. All right, so we see a few question marks, so I'll take the time to explain. Distance right now tells me how close we have the path to get to every single node based on what we've seen so far. The path to get to 5, for example, is infinity. The path to get to 4 is infinity. The path to get to 2 is 1. The path to get to 3 is 1. The path to get to 0 is going to cost us 4. All right. If that's the case, then the next nodes that we haven't visited yet, that we haven't Georged yet, right? When I say unvisited, I mean we haven't made them George yet, is node 2 and node 3. Those are the two options that we have because they both have cost 1. It costs us 1 to get there, but we haven't really visited them yet. We haven't appointed them to be George. Now, between the two of them, we're going to go ahead and pick, the node here. We're going to pick node 2. Node 2 is going to be our next George because we're going to pick between the tie break. We're going to pick the next smallest element. All right. So now George used to be 1. Now it's going to be equal to 2. Right. So we're going to go ahead and pick George the second to be 2 in this case. It's coincidental that it was 2 here. All right. All hail George the second. Type it in chat if you feel like you understand how we picked the second George. Type question mark if you're a little bit confused. All right. We got a few people who are confused. The big idea here is that we looked at distance and we tried to find all of the nodes that we haven't visited yet that have the smallest number inside of distance. So index 0 has a cost of 4. That means it takes us 4 to get to node 0. It takes us 1 to get to node 2. It takes us 1 to get to node 3. It takes us infinity to get to node 4, and it takes us infinity to go to node 5, which means that the cheapest nodes that we could visit next that we haven't visited already, the cheapest Georges we could have next is node 2 and node 3. Between node 2 and node 3, node 2 has a smaller label, so we're going to pick node 2. Right? Now we're going to look at all of George's neighbors here. George here has a neighbor in 1, a neighbor in 0, and a neighbor in 4. We're going to look at the smallest labeled neighbor first, which is node 0. And that means we get to update the distance and prev again for this, right? Because if you look at this carefully, oops. Can I select all of this? Let me try that. There we go. If we look at this carefully, the cost to get to 0 is cheaper through 2 than it is to go through 1 directly, right? If we're going to update all of George's neighbors, that's what we're doing now. We're going to update it so that node 0 now has a cost of 3 instead of 4, because it was cheaper to go from 1 to 2 to 0 than it was to go from 1 to 0. The 4 came from going from 1 to 0 directly, but now that George is equal to 2, we realize that we can actually update the cost to get to 0 accordingly, which means that the 1 here now becomes 2. And you can see here, we're getting closer to the arrays that we want on the top here, where distance is equal to 3 and the prev is equal to 2. All right, so that was us processing the first of George II's neighbors. Now we have to go ahead and process the next one, which is the cost to get to node 1 from 2. So what we're saying is here, let's just imagine we got to 2, and then we go immediately back to 1. What is the cost to get from 1 to 2 and then 2 back to 1? Go ahead and think about that for a second and then type it into chat in the next 5 seconds. It's 2, right? Since the cost to get back to 1 from 2 is 2, we don't actually want to update index 1 here because the cost is already cheaper to just keep it the way it is, right? So we don't update the cost here, even though we do look at the neighbor 1 here. And then the last thing we update is the neighbor 4, right? Because George is equal to 2, the last neighbor is 4 here. That means that the cost to get to 4 is now updated. Previously, it was infinity, right? The cost to get from 1 to 4 was infinity because we didn't have a path. And now we're going to update it to the cost to get to 2, which was 1, plus the edge cost to get from 2 to 4, which is 2. So it should be 3 overall. Someone's asking, why did we have to check the distance going to 2 and back? We had to look at all of George's neighbors no matter what. So even if we had Georged 1 before, even if we had visited 1 before, we still go back and check it just in case if the cost to go from 1 to itself is cheaper if we went through 2, which is impossible, right? But we're going to go and follow it pedantically because that's what the rules say. Now, from here, we also have to update the prev to be 2 because the path to get from 1 to 4 goes through 2. The node we visit before 4 is 2 in the path from 1 to 4. How do we add values to a path that's further than 1 node away in the algo, or is that coming up? We're about to see, right? So that was all the nodes, all the neighbors of 2. We're now going to be done there and pick a new George, all right? So in this case, we're about to finish, and we need to pick a new George. And based on the distance array, what is the node that has the next cheapest cost? We just visited 2, and before that, we visited 1. What's the next George we pick? Okay, a lot of people are typing in 3 in chat. And that is correct because it has a cost of 1. If we look at index 3, it has a cost of 1, which means that the cost to get to 3 is the next cheapest cost, and that should be our next George. So we're going to go ahead and move George up here. So, George III, long may he reign. We're going to look at all the neighbors for George. George has 2 neighbors here, right? It has a neighbor to 1 and it has a neighbor to 4. Now, someone earlier asked, how do we update nodes that are more than 1 hop away from 1? Well, we have this hop. First, we're going to check to see the node going from 3 to 1. Isn't 3 a neighbor of George II? 3 is not a neighbor of George II. In this case, there's no way to get from 2 to 3 directly. There's no direct edge, right? And oh, sorry, 3 is not a neighbor. That's correct. Oh, I see. So someone's asking, like, how did we get from 2 to 3 if there's no direct edge here? I'm not picking Georges based off of what's connected to 2. I'm picking Georges based off of what's the next cheapest thing to explore, right? So in other words, we pick Georges based on what's the next cheapest node to explore. not the next node that's connected to what we just visited. That's a really good point, right? That's a great question. I'm really happy that you asked it because it does clear up a few things for other people in the room. From the source or from George? From the source, always the next unvisited node closest to S based on distance, right? So the rule here is we pick the next node that's closest to S based on what distance looks like right now. The next closest node that we haven't visited yet is node 3 because it has a cost of 1. If you have a question, just type it into chat, or if you want to unmute, you can go ahead and do that now.
Okay, so I have a question in terms of one calling two and three, and then are we recursively calling three? And then like once we call three, three calls two. I mean, three calls four, and two also calls four. But since we already visited, we don't add that to our distance.
So we don't use recursion for this approach. We're actually just following the rules here, and you'll see how that translates into a for loop later on.
Okay, thank
Yeah,
you.
cool. So let's keep going. In this case, we're going to go ahead and try to figure out what is the cost from going to 1 through 3, right? The next thing we have to figure out, every time we look at George's neighbors, we're trying to update the distance for them if we need. So if George is equal to 3 right now, just assume George is equal to 3. We look at all of George's neighbors. George's neighbors, well, that's node 1 and that's node 4, right? Do we need to update node 1 based on going from to George and then go back to 1 from here? Do we need to update node 1? Yes or no? Question mark if you're confused what I'm asking here. But we don't need to update distance, right? We don't need to update distance because the cost to go to 1 through 3 is the cost of getting to 3, right? The distance of 3 plus the edge cost of 3 and 1. And if that's the case, then the cost here to get from 1 to 3 and then 3 to 1 is going to be equal to 2, right? And that's always going to be more expensive than the initial cost that we have, where index the cost to get from 1 to itself is 0. Now, if we go ahead and try this again, and we ask for node 4, which is another neighbor of 3, do we need to update distance to node 4 based on traversing through node 3 to get to node 4? People are typing in yes in chat. The answer is yes, because the previous, if we just compute here, the cost to get to 4 through 3, right? Get from 1 to 4 through 3 is equal to the cost of getting to 3 plus the cost of going from 3 to 4, right? And that's going to be equal to, in this case, the cost to get to 3 was 1, plus the cost to get from 3 to 4 is 1, which gives us 2. 2 here is the new cost of getting to 4. The old cost of getting to 4 costs us 3. So 2 is smaller than 3, so we want to update it, which means we update this here, and we update the corresponding array in prev, the slot in prev, to say we now go through 3 in order to get to 4. Previously it was 2, but now we know that it's cheaper to get to 4 through 3 than it is to get through 2. Okay? And then we're done with node 3. That was the neighbor that we had here. So we visited nodes 1, 2, and 3. Those were our first 3 Georges. Based on this, what is our 4th George? Okay, people are typing in 4 in chat because, again, That's the next thing that we haven't visited, which is cheap to go through, right? We visit George's based on what's the next cheapest node to explore, not by connecting with any previous traversal, right? This is different from breadth first search because instead of picking a node based on what neighbors we have, we pick a node based on the fact that it's cheap to get to right now. And just to spice things up a little bit, I'm going to go ahead and put a 3 here. Just so that we can see what happens if this were connected. So in this case, we're going to say that the next George we coordinate is node 4 here. 4 is going to be our new George, in other words. Okay, so if that's the case, George at the beginning will be, we'll look through all of George's neighbors, which is node 2, node 1, and node 5, right? Do we need to update anything? Do we need to update distance here for node 2? What do you think? Yes or no in chat. Go ahead and type it in. Question mark if you're confused. Oh, this should be, this should not be 1. This should be 3. I made a typo here. Okay, most people are typing in no. Some people are typing question mark. We don't need to update the distance because in order to get, so we're asking here, the question we're always asking is, do we need to update the distance based on the pathing that we have from 4? The real question we're asking is it cheaper? Is it cheaper to go to 2 through 4 than what we had before, right? The cost to get to 2 right now is 1. The cost to get to 2 through George will be getting to George, which is cost 2, and then taking the edge that we need to go from 4 to 2. So in this case, the cost here would be 4 versus the previous cost, which is 1. Since 4 is bigger than 1, we're not going to want to update distance because that's not a better route to get to node 2. Type in 2 if you feel like you understand the reasoning here, why we didn't update distance. Right? Again, in order to get to 2, the previous way to get to 2 only costs us 1. The new way that we're proposing is to go through 4, which means the cost to get to 4 has to be added to the cost of getting from 4 to 2. Well, that cost in total will be 4, which is way more expensive than the previous cost, so we don't need to update distance. This algorithm does assume we have no idea what the graph actually looks like. We're just going in blind, right? So if we do the same thing, we ask the same question here for node 3. Is it cheaper to go to 3 through node 4 than what we had before? In other words, can we go from 1 to 3 in a way that's cheaper by going through node 4? Go ahead and type in chat if you have it. If you're confused, question mark, right? I want to see how many of you are following along and how many of you feel confused. It's good to know what you don't know, and there's no shame in admitting it, right? I want to make sure everyone feels good about this. It is not cheaper to go from 4 to 3, right? Because the cost would be basically going through this route, going from 1 to 3 to 4, and then doubling back, which would be more expensive than just going to 3 directly, right? That's really what we're asking. So in this case, we don't update distance here as well. Lastly, we ask, do we update distance here for node 5? Right? In other words, is it cheaper to go to 5 through 4 than what we had before? Yes or no? What did we have before? What was the cost to get to 5 from 1 to 5 before? It was infinity, right? So it doesn't matter what the cost is. If there's a path to it and it's less than infinity, then we're going to update. So in this case, we're going to go ahead and update this to say that the cost to get to 5 is the same as the cost to get to 4 plus the cost to get from 4 to 5. So the cost here to go from 1 to 4, in this case, will be 2, plus the cost to get from 4 to 5, which will give me 5 total. Someone said should have been 6. I'm not sure what you mean by that. Can you clarify? And then the corresponding node here will be 4. Are you talking about the previous like edge that we had? When it went through 2 instead of 3. Yeah, the cost here, I think what we had for the cost for 4, yeah, this should be 5, I think. It goes through from 1 to 3 to 4 to 5 because we know that the previous cost to 4, the cheapest one that we had was 2. And then we add the 3 here. If you're still confused, feel free to ask a follow-up question. I'm going to move on. All right, so we looked at George equal to 4. And now we go and try to look for the new George, right? We're not done here. We're not done because we have to look at the next two Georges, even though visually we know that we're not going to update distance anymore, right? We're not done because the algorithm is blind. It has no idea what the graph actually looks like. So we have to keep going. There's no telling whether or not there's like another neighbor here that we have to explore. And so we have to look for George is equal to 0 as well as George is equal to 5 at some point. Now, the question I have for you is which George do we look at first? What's the next one we look at? Do we look at 0 or do we look at 5 here? Okay, people are typing in 0 in chat, which is correct. Someone clarified what they meant in a previous question. Let me go ahead and talk about that first. Okay, so they were saying that before we Georged 4, the distance to get to 5 should have been 6 because we would have gone 1 to 2 to 4 to 6. Or sorry, 1 to 2 to 4 to 5. And that would have been 6. All right. Let me just make sure we're clear. We're taking a pause from what we were talking before. The question was, okay, why wasn't this previously 6 instead of infinity? This node here was infinity, and then it turned to 5 immediately instead of first going to become 6 and then 5, right? So that was the question being asked. So the reason that's the case is every time we pick a George, we only update the neighbors of George. We don't update the neighbors of the neighbors of George. So when we were saying George is equal to 2, we only updated 0, 1, and 4 as a result of visiting George, setting George is equal to 2. We never got to 5 because we don't look at the neighbor's neighbors or the neighbor's neighbor's neighbors. The changes don't propagate. We literally only look at the neighbors of George each time. And it turns out, and we'll talk about this later in review, that the way that Dijkstra's and this approach looks at Georges, the ordering in which we look at Georges, allows us to guarantee that the smallest node will always have the shortest path. The next path that we pick will always not need any updating afterwards, right? So we know that we're guaranteed by the time we get to 5, we'll no longer need to update it any more times. And also that we never set the distance to 5 to be 6 because we never actually went and got to 5 to update it by going through 4, right? We were forced to go through 3 and 4 first before we could ever get to 5, all right? That was a really good question. If you don't know what I mean, feel free to ignore it, but someone asked a really insightful, good question about why like infinity never became 6. And the short answer is that when we looked at 2, we only updated the neighbors of 2. We never updated the neighbors' neighbors, okay? But it was a really good question, so I had to stop and answer it. All right, so we're going to go ahead and look at 0 here. We know that 0 has neighbors in 1 and 2, right? George is equal now to node 0. George's neighbors won't be updated because George's neighbors here, I'm going to go a little bit faster. George's neighbors here are now the cheapest that they could be, right? We're going to look and say, okay, what's the cost to go from 0 to 1 through 0? Well, the cost will be the cost to get from 1 to 0, which would be 3 here, plus the edge from 0 to 1, which would be 7 total, which is way more expensive than the 0 that we already have. Likewise, to get from 1 to 0 and then back to 2, the cost would be more, so we don't update distance here. All right. So someone asked, why did we pick 0 here instead of 5? We picked 0 as the next George because we only had 5 and 0 as the next unvisited nodes. And between the two of them, 0 was cheaper to get to than 5. But now that we've went ahead and visited 0, we're going to go ahead and move now to this 5 here. Right? That's the last George that we have. All hail George V. All right, so from here we have the same thing, right? Let me just spell it out in detail. We look at all of George's neighbors. George's neighbors in this case. What node is George's only neighbor? This George is kind of very solitary. It only has one neighbor in this case. George only has node 4, right? Because if George is equal to node 5, then it only has node 4. And we're asking, do we update distance here? In other words, is it cheaper to go from 1 to 4 through 5 versus the previous, versus what we had before, right? The cost to get from 1 to 5 and then back to 4 is the cost to get to 5, right? In other words, the distance to get to 5 plus the edge cost between 5 and 4. Well, that's actually just, 5 plus 3, which is 8, which is going to be more expensive than what we had previously, which was just 2, right? So we don't update here. We don't update the distance to 4 based on this line here, right? When we look at George's neighbors, we update the distance if they're needed. In this case, we didn't. And now we're out of George's. So we're finally done. And you can see here that the distance array looks exactly like what we wanted originally, 3, 0, 1, 1, 2, 5. Sorry, this should be a 5 now because I added an edge in the middle of the class, in the middle of the demo. And then the prev should be all of the nodes that we can visit, that we visit right before the node that we care about. So in order to visit 0, we had to go through 2. In order to visit 1, we didn't have to go through anything. In order to visit 2, we had to go through 1. In order to visit 3, we had to go through 1. In order to visit 3, we had, in order to visit 4, we have to go through 3. And in order to visit 5, we have to go through 4. All right. That was a lot. I'm going to go ahead and let's take a 5-minute break now. And then we'll come back and look at the actual code for this, which I promise, well, we'll see how it goes. Let's take a 5-minute break. I want to show you a very cute cat picture during our break. So let me see if I can do that easily. So we got a shrimp pillow, a neck pillow. I don't know if we saw that in this class, but we tend to put the shrimp pillow near the cat or on the cat. And for whatever reason, life imitates art in this case. Just to double check, we end in like 8 minutes, don't we? Oof. Going through Dijkstra's is always a challenge because if I want to go through a tutorial on how to solve Dijkstra's, we end up with a lot of time being spent. So I guess we'll all take a breather here for like another minute. I was going to say a 5-minute break, but I think we need to actually look at the rest of the code. So we're gonna need to handle that. All right. When will the regrades be done? I should have them done by the end of today. Between preparing for your next exam and grading your current exam and some things that are going on with my family's medical situation, I've been a little bit behind on things, and I apologize. That's definitely my bad. But there's just been a lot going on. So you should get your final grades tweaked by the end of this week at the very latest. Most of you shouldn't see that big of a change. It's either like a slight change up or a slight change down. There were some typos in the rubric that we used. All right. Let's go ahead and take a look at how we actually solve this problem using code, right? What we had before was this crazy idea of picking a George and then like running with it. Now we have to actually think about what this looks like in real life. So go ahead and type in code in chat if you're ready to go back into it and try to solve this together. And we're not going to go through a demo. We have no time. We're not going to be able to get through this in time. I tried this with the previous section. We ran out of time. So this section, we're not going to push it. We're going to try to solve this one step at a time. So in this case, the intuition is that breadth first search kind of works in the case where all the nodes, all the weights are 1. Because if you think about it, breadth first search goes, and let's say we started at this as our source. We're going to look at all of the neighbors. And then we're going to look at all of the neighbors, which is just 4 in this case. And then we'll look at all of the neighbors, and then all the neighbors, right? And then we can't visit here because we'll not be able to find an edge that gets to 7 or 8. And so breadth first search kind of works the way what we want. And you are expected to know breadth first search from the homework. So we covered it as a demo in class. And then on the homework, the code for breadth first search is right here. Right, so right here, we expect you to understand what this does. We have a queue, we add to the queue, we have a visitor array, and we process it accordingly, right? The key here is that if you look, if all of the nodes were 1, all of the edges were 1 rather, that's the same as saying, okay, well, all the nodes that are 1 hop away will have a distance of equal to 1, right? All the nodes are 2 hops away will have a distance of 2. All the nodes that are 3 hops would be 3, and all the nodes that have 4 hops would be 4, right? If we could kind of hack breadth first search to take into account the edge weights, then we would be able to actually properly iterate through all the elements and visit all of the nodes and properly like have distance and prev updated. Now, this is very vague, so I'm just going to go ahead and give you the intuition, right? When we add to the queue, we want to account for the weights. We only want to visit the next cheapest node, right? We're very miserly in that way. We're very greedy. We want to only visit the next cheapest node that we haven't visited before. And that's similar to how breadth first search works. We visit the next cheapest layer, which is the neighbors of S initially. And then the only thing that's cheaper than the next cheapest from that is the neighbors of the neighbors of S, then the neighbors of the neighbors of the neighbors of S, and then the neighbors, right? So the same thing applied here when we were going through our silly approach of picking George. We only wanted to visit the next cheapest node that we hadn't visited before. And the way we want to account for that is when we add to the queue, we want to make sure that the size of the weights, the cost of the weights are accounted for when we add to our queue, right? This is effectively what a priority queue is always used for, right? So if you haven't seen a priority queue before, type no in chat. Otherwise, type PQ if you've seen this before. Okay, we're seeing a lot of no's in chat. All right. This is something I really wish 2720 taught, but apparently they don't often teach it. So it's okay if you've never seen this before. But a priority queue, what you need to know is that it's a queue, so first in, first out, but you add each thing through a priority key. The queue stays sorted by smallest first, so the thing with the smallest key is removed first, all right? So add, it has 3 methods. It has add, it has delete min, and it has decrease key. Add will add a thing to a queue, inserting it into the right place based on its key. Delete min will be the next smallest priority key and returns the associated thing. And then decrease key will update an existing key in the queue and resource the queue. The easiest way for me to explain this to you is through an example. So let's say PQ is equal to a new priority queue, which is empty. If we say PQ.add And the first argument is going to be key. So let's say we added 3 comma foo, and then we say pq.add of 2 comma bar, and then we said pq.add of 5 comma baz. What we'll see in our priority queue is that at the very beginning, it's empty. From there, we're going to go ahead and add 3 comma foo into our queue, right? Now we're going to add another element, which its key is smaller than the previous key we added. So we're going to put the 2 comma bar at the beginning of our list, followed by 3 comma foo, right? If you feel like you understand what's going on and kind of the idea that this stays sorted, then what happens when we add 5 comma baz? Go ahead and take 5 seconds and then type it into chat once you have it. Does it go to the left? Does it go in index 0, index 1, or index 2? If we're adding 5 comma baz here, type it in chat if you have it. It should be the rightmost, so index 2. So we have 2 comma bar, which is here from before. We have 3 comma foo, and then we have lastly 5 comma baz. Okay. And if we wanted to update, let's say we said pq.decrease key of baz to say it's 0 now, then what will happen is we'll resort this list. Now that baz has a smaller key, it needs to go in front. So 2 bar is here, and then 3 comma foo is here. Okay. The important thing you need to remember is that you can use a heap, min heap that we saw in lecture 6 to build this. And the key to remember is that the add operation is log of n, the delete min operation is log of n, and the decrease key operation is log of n. All right. So I'm going to very briefly show you the code and explain how it relates to what we were doing before. And we won't have a time to go through an example. I'll record a video of us going through the code a step at a time. And then you'll have homework between now and the exam to practice Dijkstra's before the exam, right? Promise, I promise, I promise. Homework should be not scary compared to the programming homeworks, right? It's going to be similar to the homework that you just did that's due today. But we need to go through Dijkstra's, and this is the only way I know how. So we have to have homework going into the exam week next week. I apologize. We have to do it anyways. All right. So here's the code on the left here. This is the pseudocode I want you to know. We know that we have a graph as input and a source S. We know that all the edges are positive. And then we're going to output distance, which is going to be the distance to every single other node that we can reach. And also prev, which is the path, the previous node that we visit before we visit that specific node from S to that node. All right. So at the very beginning, we're going to start with a bunch of infinities and a bunch of nulls, right? Prev will be an array of size v, and it'll have a bunch of infinities in it. And distance will be a bunch of infinities, and prev will be a bunch of nulls. And then at the very beginning, like we said before, distance of s is equal to 0. We get that for free each time. Then we make a priority queue here using the distance values as keys. And while that priority queue is not empty, we're going to pick a George. We're going to pick a George. That's what this line means. U is equal to delete min of H means we take the next smallest unvisited node and we pop it off our queue. From there, we're going to look at all of the neighbors, right? And we're going to update the distance for them if we need to. If the cost to go to node V, which is the neighbor here, is cheaper through George than it is the previous cost to get to V, then we want to update distance, we want to update prev, and we want to decrease the key. Afterwards, since this is a for loop, we'll pick a new George. Since this is a while loop, we'll pick a new George. All right. This code is exactly what we were doing by hand previously. Hopefully it isn't scary. I know it looks scary, but once we go through step at a time in the video that I'll post, hopefully it will become less scary. But I'll leave it here because we don't have time to go through everything, okay? So what I want you to realize is that when George is the next unvisited node based on distance, that's the same as saying, give me the next smallest element out of my priority queue. When we look at all of George's neighbors, that's this for loop here where we look at all the edges from George, which is U, to its neighbor, which is V. Now, if the neighbor, the cost to get to the neighbor is cheaper than the cost we had before, which is what this line says, then the distance is updated, the prev is updated, and we update the priority queue and resort it so that George will always be the next smallest thing that we have. All right. We're going to pause here. I know some of you are still confused. We haven't looked at the runtime, and that's okay. Weighted graphs add values to edges. That's what you need to know first. We can represent edge weights in code by adding a little bit more information to matrices and lists. We'll see that in the homework. And the most important thing we care about for weighted graphs is pathing, the idea of getting from A to B. Single source shortest path is the canonical way we solve this problem, and Dijkstra allows us to find the solution to this problem with graphs with only positive edges. It's essentially a breadth first search with a priority queue, which I alluded to earlier, but you might still be confused about, and that's okay. Exam 2 is next week. It's going to be on trees of all types, graphs of all types, and algorithms on each. You can go on Piazza, and you see here that all of the information that we have is here. And you should take a look at the Piazza post if you haven't already. Everything you need to know, including resources on how to study, is linked. All right. This is all we had for today. Thank you so much for being patient with me. I will see you all next week. Take care.